HomePlug AV2. So we discussed this last time. I'm going to review it. Basically, AV2 products are available right now. In fact, as I said, they're not very expensive, and they give you 500 megabits advertised. 600 is written here, but I saw advertisements of 500 on Amazon and so on and so forth. Anyway, so you can do lots of video on those. And the way they get that high bandwidth is by several things which we are going to talk about, but the biggest thing is having more spectrum. The previous version went from 2 to, anybody remembers 2 to what they went? 2 megahertz to what megahertz they went to make how much megahertz? Nobody remembers. Then basically 2 to 30, it was 28. Now they added another 56. So if you have this much megahertz right there, you have 2 or 3 times the previous capacity of 200 megabits. And then they added MIMO. Now this is another interesting concept. MIMO you all know in wireless, but how do you do it in the wired network? And this one they did by basically having 2 pairs rather than 1 pair. So you transmit on 2 different pairs and then combine the signal at the other end. Whereas in the wireless we have multiple antennas, and then we receive many different signals and we combine them. Here it is wired signal. And so basically they use 2 pairs. One is between line and neutral. So actually there are total 3 pairs because there are 3 wires in a power line. And so if you make a pair, you have 3 pairs. And so you could use any 2 of those 3. Beam forming is that basically for each transmitter you will have we already did before adaptive bit loading, but now we will have to do it specifically for each receiver as well. And so you just concentrate on that receiver as opposed to having one kind of noise level for each receiver. You will have total maps for all the receivers, separate maps for all the receivers. Lower overhead, and this actually should probably not make any big difference compared to what we have done here. Is like they have factor of 2 or 3 in the bandwidth here and 2 in the MIMO and so on and so forth. This one is just reduce the header size and so on and so forth. Efficient notching, and I think we had discussed this last time. If anybody remembers what is a notching. Yeah, remove some particular part of the spectrum when there is a lot of noise there. Previously it was a fixed size, and now it is very efficiently done as to depending upon what the noise level is, they just reduce that much. So these are 5-10% range improvement, the last ones. Repeating, and the repeating is that the signal is repeated. Repeating means digitally amplified, means that you bring it back from analog domain to digital domain, make 0 and 1 bits and then transmit it again on the wire fresh. So that way it can go longer distances. Better coding, and so 12 bits per hertz. So we were talking about previously some 4, 5, 6, 8 bits. 12 bits per hertz can give you a lot. And so now with that, and then the code rate is 8 by 9. Code rate is how many bits you put extra for ECC and error correction and detection. So you just put 1 extra bit for each 8 bit. So the code rate becomes 8/9. Power control, and the transmission power is again just like the spectrum is managed, this power is also managed. The level of the signal is managed to each receiver so that it is optimal. And power save, that was another thing, is that the energy has to be saved. Even though there is plenty of energy at the power outlet, they want to make sure that the stations can sleep, because that is what they are doing most of the time. Like in my home, I have put those power plugs. I don't think I have used them in 2 years. So they could be in a room ready to use, but people don't use them, and so it is better they're sleeping than awake. All right, so that was AV2. The next version of HomePlug is called GreenPHY. And GreenPHY goes in the other direction. while AV2 goes into high throughput area, GreenPHY goes into low throughput area. And the word green clearly means that here emphasis is on energy rather than throughput. They want to minimize the energy, and so it is designed for home area networks for monitoring and control of energy consuming devices. So basically this is monitoring and controlling, right? So one of the biggest energy consuming devices soon to come out is the electric car. Electric car needs a lot of power for charging, and you really need to coordinate with the energy company as to what is the right time to charge, and so that there is the right price for you to charge. And so all that will be done by these smart chargers, which are connected to the internet and can control your device charging. And the same thing will be actually used at the charging stations. For example, there is a charging station here in Washu, next to the energy department actually, where the cars can be charged. And right now they are not connected to the internet, but I'm sure someday they will be connected to the internet, and there will be proper charging, and by charging I mean proper dollar charging. Right now probably, I don't know, I mean I haven't used them, but I'm sure that probably right now Vashu is just showing it off rather than making money out of it. So all that thing, and including all other devices, will be done. So for that we need a very low power, low data rate version of HomePlug AV, and low cost. So those are the three things: low cost, low power, and low data rate. And so this is GreenPHY actually cuts out all the frivolous stuff and reduces the cost, power, and as a result data rate as well. So the HomePlug is covered by 1901, and so is the GreenPlug, HomePlug Green. So this is just one of the profiles. So we already saw HomePlug AV, HomePlug AV2, and HomePlug GP now. This is the green power. They're all part of the same standard, 1901. And each standard has a profile. So what happens, what is the profile? Basically what the standards do is, they generally have many options. Alright? And different companies can decide to implement different options. However, if everybody decided their own options, then they won't be able to talk to each other. So what they do is they set up a profile. They say, okay, like here's a group A, there's a group B, there's a group C. So you select one of the groups to implement. And everybody who selects implement group A selects group A. That way they can talk to each other. So AV is a profile, AV2 is a profile, and GP is a profile. Understand that difference? Right? Profile means a whole set of options that are implemented by this one. And interestingly enough, these are all compatible, theoretically at least, in the sense that AV2 can listen to AV and understand it. And AV can basically slow down AV2 to bring it down to AV, so they can talk to each other. Alright, if they need to talk to, they can bring it down to the lowest cost, just like lowest denominator, just like it happens in Ethernet. If you connect a 10 megabit Ethernet device to a 100 megabit Ethernet device, they can still talk, but they will talk at 10 megabit. Right? Same way here. So now 28 megahertz. So this one uses 28 megahertz GP. That was 2 to 30 megahertz just like before. And it only produces 256 kilobits to 10 megabits. Okay? And it only uses one modulation. One modulation. So the lowest modulation, if you remember the modulation list was given here. This is the lowest modulation, BPSK. It gives you 2 bits per hertz. So you just used one, period, done. Simplest one. This is cheapest one. It doesn't require too much of work, so that's how it can be cheap. Alright? And so one modulation and no tone maps. And they don't try to store tone maps, that saves on memory as well. So it uses 75% less power than AV and 75% less bill of materials. Bill of materials simply means the components inside it. So when you make a GP board, it has 75% less components than a AV or AV2. So the device coordinates the sleep cycle and may sleep for 2 raised to n beacon intervals. Alright. So what happens is, beacon is what decides the synchronizes all the clocks. So everybody says, okay, now this is the beacon time, the coordinator sends the beacon, and then somebody can say, well, I'm going to sleep for every 16 beacons and then wake up every 16th beacon. And so it will set a timer itself, turn off all its circuitry, go back to sleep, no energy is consumed. It will come back every 16th interval, and in the beacon then, the coordinator knows that this guy is going to wake up. Now, it will have information whether it has any packets or not for him or her. And so it will inform that there is a packet for number 13. Number 13 has already woken up, heard the beacon, and then it says, okay, send me that, and then it will be given, and then it can go back to sleep. This is actually what is done in all wireless networks, including on your cell phone. Your cell phone is mostly sleeping. But the cell tower is transmitting beacons, and the cell phone tells the cell tower when it will wake up, and then the cell tower announces whether there is anything happening for that phone. Okay? And that's how the battery times, charging times have gone up in the past few years. Not because the batteries have become any better, but the batteries have become some better, but they are not by as many factors as the sleeping has become better. So the devices coordinate their sleep cycles and may sleep for 2 raised to n beacon intervals, for n is equal to 1 through 10. So you could sleep for 1000, 2 raised to 10 is 1024 beacon intervals, and then wake up. HomePlug GP 1.1. So GP was the first one, and 1.1 is the next version. Adds new power management features and for electrical vehicles. So electrical vehicles needed some extra features which are not required for normal devices, and in particular secure billing was one of them, is because there's a lot of money involved in charging the electric vehicle, so they want to make sure that nobody can steal somebody else's information, and so that is possible by GP 1.1. All right, and I must remind you that basically HomePlug is very well documented by the HomePlug Appliances, HomePlug Alliance's white papers. If you go to the website, you will find one white paper on each of these devices. You will find one on AV, one on AV2, one on GP, and those are required readings. You should read them. Now, they don't stop right there. After that, they come to combine many different technologies into one. So if you have a home which has wireless, which has HomePlug, and which has DSL and everything else, and you have Ethernet, right now you cannot switch one to the other. Right now everything is separate. So if you are working on Ethernet and you want to move to wireless, you have to just disconnect Ethernet, restart the whole thing, whatever you were doing on the wireless. There is no coordination. The wireless doesn't talk to Ethernet. Ethernet doesn't talk to wireless. You cannot just transfer your TCP connection from one to the other. You have to break the connection, restart the connection. With new standards coming up, the media should not matter. So that's what it is that we have a Convergent digital home network where you could have many different devices, many different technologies, and they could talk to each other. They will be able to talk to each other. For example, wireless can talk to power line devices. And so that for that there is a standard coming up called, actually there is a standard already which is called 1905. So IEEE 1905, and what it does is it puts a layer between the IP and the data link layer. So now really the data link layer becomes totally hidden in that sense from IP. Okay. So the entire home looks like a single data link, single network with automated provisioning, management, and operation. So basically, as we'll show in the next slide, basically all of these things can be managed together. So basically whether it is 2.3, 11, power line communication, or coaxial cable, all of these can be done with one set of protocols. Allows a device to aggregate throughput from multiple interfaces, and that's another thing you could do. You could use them in parallel. Right now you cannot do that. So when you transfer a file, either you use wireless or you use wired. With that you can do parallel. You could do coming on both. A link can be used for fallback when the other link fails. Backup links. So you might have a wireless link which you really don't want to use because it's so slow speed, but if your wired link fails, this will take over. And an abstraction layer, which I already talked about, is used to exchange messages which are called control message data unit, CMDU, control message data. So this is the layer, and this talks to the other devices, and those messages are called CMDU. And no changes to underlying protocol is required. So we don't change 802.3, 11, PLC or MoCA, or we don't change IP. We just change this layer in between. So what it is that basically there is a protocol called ALME, Abstraction Layer Management Entity. So this is there is a ALME protocol, and so the messages which are being sent are called CMDU, as we said before. So every device has this. Now the devices can talk to each other regardless of what data layer you have. So a wireless device can talk to a wired device. A wireless interface can talk to a wired interface. And so basically all the interfaces can talk to each other. So ALME allows neighbor discovery, topology exchange, topology change notification, statistics measurement, flow forwarding rules, and security associations. I think all of these should make sense as to what it means. For example, what is neighbor discovery? Anybody?
There are other devices that are
in the same area. So for example, you want to know in your house whether you have wired device, Ethernet can find out whether there is a Wi-Fi device, right, and vice versa. That is neighbor discovery. Topology exchange and how they are connected, topology change notification if something goes down or up, and so on and so forth. All right. And for example, AV can be used as a backbone. This is just an example here. And existing 802.1 bridging protocols are used for loop prevention and forwarding, and everything else that was there before can still be used. So there is some more coordination basically between these technologies. So now we remember we have two protocols. 1901. What is 1901 for? Anybody heard that number before? Nobody heard that number?
GP version of.
That is HomePlug. All those versions of HomePlug are 1901. And then we had 1905. 1905 goes on the top of 1901. 1905 is this abstraction thing. Okay, question.
You have all these devices that are communicating over the power line. Couldn't someone hook into your smart meter and get all your traffic?
No. Okay, so the thing is, like everything else, there are two things that you need. One is you need physical security. I mean, if you leave an Ethernet port outside your home, anybody can connect, and so that is bad, right? So physical security is required. Now, even if, let's say in a public place like this, and there is a power plug here, if I connect it, I won't get any signal. Okay, because then there is a protocol security which does authentication, right? So all of these have protocol security, but on the top of that you really need physical security, because if you just have protocol alone, then there is more chances for the people to hack. All right, good. So talking about security. So 1905 basically allows security configuration, and there are three methods of security configuration. One is a push button. So whenever you push that button, they start looking to talk to people who are not really secure. So that way nobody can just come and connect to your network. They have to connect at a time when the device has some other device has a push button pushed. So when you have push button pushed on two devices, then they can talk, even though they are insecure. They can exchange some information saying that your button has been pushed and that you are the device, and then they can exchange security keys for the rest of their life, right? And so that is one way to change. So that is basically what you do. You buy some device from the market, bring your home, push the buttons. Now that becomes your device. So your neighbor cannot listen to your devices because they cannot push the button at the same time. Right? Your neighbor also brought a device with you from the same store, but the time when they push the button, you don't know. Understand that part? Second is you can configure a passphrase key. This is similar to what you do on Wi-Fi. In your home, you put a passphrase and you use that on all your devices, and nobody knows your passphrase. They cannot use the same devices. So now this one is, in that sense, if they find out, then they can use it. So it's not time sensitive basically because this is the key. And so just like any other password, you're supposed to change it every few often. So if somebody did find a passphrase, they won't be able to use it again. NFC is the near field communication. And that is, you must have heard about near field communication. In fact, I have few slides right after this. Is that you can bring two devices close to each other and they can talk to each other. So that is one thing, is that if they can communicate through radio and then exchange the information because they're so close. But obviously when you bring the devices, it doesn't mean that if you just stand next to somebody you can get their secret. In addition to that closeness, there is some other action will be required, some other secrets will be required, some other smartness is required before that exchange can happen. So that is NFC. And then auto configuration. So basically the access points, I think basically this is the same repeat of the previous three methods, is that you bring a new access point in your home or in your company, you put it on, and then you go and it will auto configure. It will get most of the information from the network itself except the key part, and then you have to use one of these methods to do that. For example, you could use passphrase, or you could have a push button, or NFC. So there is a program for the devices are already becoming available for 1905. I have seen them actually at least in the HomePlug advertisement, dealing devices and things like that from different companies. And so those have to be certified that they are compatible with the rest of the industry, and that certification program is called NY. I don't know why the name is or what it means. It's just like Wi-Fi is the program for certification of 802.11 devices. NY is the name for the program for the device certification for 1905 devices. So what will happen is when you go to a market, you will see NY certified. And then they won't say 1905 certified because that is very abstract. Nobody will understand that. But NY will become a famous word, and then you will start buying NY. And Qualcomm calls its technology Hi-Fi. And so they are not using about NY, but I'm sure NY is industry standard, while Hi-Fi is just one company's name for it. Any question about that? Yeah.
Yeah, I mean, the Wi-Fi and the HomePlug have their own security methods. So what's the relationship with this one?
Right. Okay. So the question is, each of these devices, each of these data links, Ethernet has its own security method, 11 has its own security method, and PLC has its own security method, and then this 11 has a security method. And each has its function too. The thing is, if you are going to use 11, if you are going to use 802.3, you need to pass their security gate. However, if you are going to come through wireless, you have to pass wireless security gate 1905 and then get into 802.3. You have to pass 3 gates. Okay? Because if you just went straight to 802.3 means you plugged it in, you are not using 1905, you are not using Wi-Fi. You don't have to worry about them, right? You don't need their key. On the other hand, if you're going to come through Wi-Fi and you want to use my Ethernet, you better have 3 passwords. I mean, you have password for Wi-Fi.
Yeah,
I mean,
that makes things complicated.
No, I know. For the user, security is always a problem. But the thing is, you basically, one can design a system which I don't know, I mean, like probably independent of all this, which is actually right now used in the real world, where they call it single sign-on. Right? You sign on to some system which will give you permission for all of the other systems. You sign on Facebook and you can do shopping in Amazon. That's what is happening right now, right? So single sign-on security is there, right? So one can do that too, but that is independent of all this. All right, good question. All right, then there is one more program what do we do outside the home? So far we were talking about the home area network, but outside the home for meter reading and for other things, the power company needs the communication, right, with their own devices, and so there is a long range outside the home power line communication. So there is a standard for that too, and that is called 19.01.2. 1901.2, and that communication is somewhat similar to what we discussed 19.0.9 for PLC, but slightly different because it is low frequency and narrow band, and because narrow band means they don't use 80 megahertz. And so that program is called Netricity. Again, there is a standard and there is a certification program. So Netricity is simply the certification program. So if somebody implements 1901.2, they could claim that we implement 1901.02, and they could write that in their standards. But if they're certified by HomePlug, which is actually doing Netricity, then they can say Netricity certified. All right. So this is a certification program which is given by an independent organization, and it's better to just go with those terms than go by the standard, because the standard allows a lot more flexibility. Netricity guarantees that you can work with some other vendor's equipment. Okay. All right. Now you go to the new handout, and while we are at the data link layer, I thought I will just talk about few more data links which are very commonly used. So those are in this new handout. Slide number 30. One of the common ones is called Fieldbus, which we have never heard of. Before, but basically Fieldbus is very common. And so what is a Fieldbus? Fieldbus is a family of protocols for short range. Now here is the keyword: short range, real-time distributed industrial control systems. Short range is 13 kilometers. Okay, so basically, if you want to control any manufacturing plant, inside the manufacturing plant you want to control anything, you use the Fieldbus, and the name Fieldbus basically says that, right? It connects the programmable logic controllers to sensors, actuators, motors, lights, switches, valves, and so on and so forth. And the main thing is that to connect to all of these, you don't need to take wire to each of them. You don't need to take a separate wire to each of them. You can just connect all of them to the same pair of wire. So it's like a bus. Okay? And so that's the reason they use it, is because now you can just have the wire go around the building and everybody is connected to that. And when you have such a thing, then we know how to use it, and that is we call HDLC or SDLC. Anybody know HDLC? Yeah, but what is the main thing is master slave, right? In HDLC, what you do is you have a master, everybody else is a slave, and then when somebody wants to talk, basically master has to ask, do you want to talk? Go ahead and talk. So basically that's how the hundreds of devices can share this bus, because there is a master which controls the timing, who can talk. All right, now I'm not going to say too much about Fieldbus. I just wanted to introduce the name here, because if you really needed to use it, there is plenty of information at many places, including Wikipedia. But what it is, it's not one bus though. Key thing that you need to know is that Fieldbus in different industries are different. So Aeronautical industry will use a different kind of field bus than the car industry, than the power industry, and so on and so forth. So when they sat down to make a standard, they couldn't make one standard. So there is a standard which is called IEC 61158. It's a standard, but it is 4,000 pages, consists of 8 different standards which are totally incompatible. So being compliant to this standard means nothing, but at least you know that these 8 are standard, because there are 80 others which are not standard. And so basically, and the second thing out common about these different ones is that they only cover PHY and data link and the application. They are one-hop protocols. That means that you can talk to any device using these protocols. PHY, physical layer, data link layer means messages, and that's it. There is no routing, nothing. And the messages have some meaning. Messages might say the link is down, the light is up, the light is down, light is turned down, or 50% up, things like that. So this is application is sitting right on the top of the data link. So you cannot really go 2 hops. There is no routing concept in that sense, right? It's just a bus which you use it right then and there. Yeah.
How is what's the physical existence of this Fieldbus? How is it connected by devices?
Okay, so basically they have wires going to different devices, and then just chain, daisy chain. Is that answer your question? What is your question?
It's dedicated wires.
Okay, I wouldn't call it dedicated wire because it is shared wire, right?
Shared is, I mean, right. I mean, the elements on the bus share that bus, right?
Yeah.
Does this thing have anything to do with that?
PLC. Okay, no. Okay, all right. This is not PLC. Fieldbus does not use PLC. Fieldbus uses physical wires, which have different. So there are 8 standards. Each of them have a different meaning of the bits, right? And each of them has their own PHY layer. So they will have their own way as to how to, what does 0 mean, what does 1 mean, things like that, right? So this has nothing with PLC.
Right. If you have wires connect everything, you have these 8, compatible.
Incompatible protocol.
Incompatible types. And what's new about this? I mean, protocol like this has been existing forever.
Yes, there's nothing new. No, hold on. This is old stuff. First of all, this is not new. I just wanted to introduce the word because if you know about Internet of Things and you don't know some of the key things, it's like this. You know about virtualization, but you don't know VMware, you have missed half of the story, right? So that's why basically this is incompatible. I'm not spending any time on this. I just wanted to introduce the word Fieldbus and tell you that this is the previous world. The newer world actually is right here, the next one is Industrial Ethernet. So we found out that there is a problem with the previous one. First of all, they are incompatible. Second of all, they don't have any routing. So you really have to be there. You cannot be controlling from here a plant in Japan, right? Because there is no routing. With this Industrial Ethernet, you get over all that issue, right? So what is Industrial Ethernet? Industrial Ethernet is same as the regular Ethernet. So there is no new standard for it. But the devices are industrial strength. The devices are something that can stay in big heat, big temperature, outside, outdoor, things like that. So they don't just, because the water, or rain or something like that, they don't, misbehave. So that's basically the industrial part is the device strength, the packaging. So Industrial Ethernet is same as regular Ethernet, but with rugged connectors and designed for extended temperature, humidity, etc. environment. And second thing they don't use is the CSMA CD, which is kind of a standard anyway. So basically they use full duplex, which means they connect the wire to the switch, which is what we do at home too. So CSMA CD was kind of always dreaded upon by the industry because they didn't want to have randomness. With this full duplex, there is no randomness. And they generally use optical fiber rather than electrical wires. Why optical fiber? Because optical fibers are not affected by big electrical magnetic fields that happen in the industry. Alright, so that is third feature. And fourth feature is basically, it's actually not a feature, fourth is a problem. The problem with Ethernet is that the minimum packet size is 64, and most of these devices need 1 or 2 bytes to be sent. So they have to send buffer, they have to pad. The padding is bigger than the information. Right? So that's the only negative. Ethernet was designed with certain things in mind. At that time they felt 64 byte was good enough. You would never want to send anything less than 64 byte, but now it is being used for places where you just want to send 1 or 2 bytes. So you have to pad up to 64 bytes. That's the negative part of it. But this is where the world is moving, yeah.
64 bytes in here is ahead of the size of. So why did you buy the 64 bytes here?
Oh, okay. So basically, you cannot send any Ethernet frame which is less than 64 byte by the standard rules. Okay. That 64 byte will include, of course, 6 byte of source, destination, and whatever else you have. But the minimum has to be 64 byte. If you have, let's say you want to send 1 byte, you have to put all the header, and let's say the header became 18 bytes plus 1, 19 bytes. Okay? You have to add padding to make it 64. Okay, anybody knows why you need minimum size? Why couldn't this make it 32 or 10 or 5? Huh? Yeah, perfect. That's the perfect answer. Is that if you have very small frame and I may transmit and the other person at the very end may transmit, we both may transmit but will not detect the collision, because by the time his packet comes to me, I've already done and gone to sleep. So we want to make sure that the packets can go end to end before your packet is finished. If the end to end was 2.5 kilometers, then they calculated for 2.5 kilometers how much do we need, how many bits we need to fill up that one at 10 megabits at that time, and finally the calculation came out 64 byte. Right? Now if you were to do it for higher speeds, you will have to increase that minimum size accordingly, right? But what they did was, instead of changing the minimum size, they changed the distance. Instead of 2.5 kilometer, as you go higher speed, at 100 megabits, you go only 250 meters. Even if your electrical signal will go farther, but protocol will not allow it. Okay? Industrial Ethernet. Now then there is another standard, which probably the last standard that I want to introduce today is 1451. Now these are all the standards which normally we don't teach in the networking classes, and they have been around for some time. But now that IoT is coming, we have to know about these things, right? So this is a protocol to query the devices, transducers, query about their properties. So basically what this is that each transducer has a memory device. So basically they keep something in the memory which tells what they are, who made them, and things like that. And so how do you query them? So there's a standard 1451. And so this defines the messages that they will understand and the responses that you will understand. And 1451 is simply a protocol to query and get the data sheet from a device. Basically, that's all that is. And it is based upon XML. So basically the manufacturers can explain what that means. Basically they could have the definition in some place, and then when you get the response saying, okay, get the definition from Cisco and here is my response. And then you can combine the two and make sense out of what it is. Okay? All right. Then another thing which is related to the Internet of Things is the smart cards. Now, basically we have talked about smart devices, smart appliances, smart meters. So what is smart? Smart simply means two things: computing and communication. Right? We talked about cyber. Same thing. So a smart card has some computing power in it, has some processor in it, and it can talk. Right? And we carry those cards in our pocket every day. So when you carry a bus card or a train card and a Vashu card, Vashu has given you some cards, those are all smart because they have a processor inside them. smart card. So the processors look like this, I mean, there's some kind of weird printed stuff, but basically they might have capacitors and inductors and then some chip. And so what happens is when somebody wants to read them or talk to them, there are several ways. One is that they could send a wireless power that powers up the device. The processor wakes up and produces the answer and then transmits it. So it doesn't really need the battery. Yeah.
This may be a stupid question. What do you mean by processor?
CPU.
I mean, for a car, you have a CPU, a memory, you have a arithmetic unit.
Yeah.
For all cars?
Yeah, very small. So the thing is, it doesn't have to have 2000 instructions. It could have a simple instruction which says read the memory and send it out. All it has to do is send a number. So yes, there is a processor. In fact, your SIM card is a very smart card, in your phone. It has a processor inside. You can see the processor actually.
Okay, and
your bus card has a processor in it.
well, even for your subway car, right?
It has that processor.
So
So the processor costs $5-10, $0.05-10, right?
Right.
So I mean, they are not very expensive like x86 or x84. They are very simple things, which can do some simple things.
So still we call it a smart card, and there is a processor. We call it a processor.
Because they have processing power and they have communication. Yeah.
It's passive device.
Now, okay, you use the word passive. I am coming to that word. All right. So, smart all means is with a processor. Now, of the smart cards, RFID, what we have heard, is actually a subset. All right. So the RF, if they use RF, then we call them RFID. But first of all, they don't have to be, card doesn't have to be an ID, and it doesn't have to use RF. All right. So a smart card is a bigger class of things than RFID. Now RFID is what is shown here on the right side. RFID basically is you have a reader and you have a responder. Right? Reader is powerful. Reader has a big battery or big electrical current into it, and it can send a lot of power. The responder has nothing in it. Right? So that is what is done. Basically, when you pass through a toll booth and the toll is collected, actually in the toll booth when the toll is collected, that is actually not passive. That is, both sides are active. The toll booth has a lot of power and your car has a power, and they talk to each other and they are done. Right? The transmission exchange takes place. Bus, rail passes, passports. When you get a US passport now, it comes with a RFID, and they can just read it basically. And the interesting thing about that, this is a really powerful processor in your passport, is that they can see your picture, not what is pasted in the physically, what is in the memory. All right. So what you see physically is, you can change it, but that doesn't change the real information. It's very difficult to change the real information. So that is the use of RFIDs. Now they have an active, passive, or semi-passive. If they have a battery, then it is active. So an active one is, this car keys. This is an active RFID, right? I mean, this one has, you press the button, there's a battery inside it, car opens. So that is this is active. Passive is what you buy from Walmart. When you buy a shirt from Walmart, it has an RFID. If you take it out the door, it will buzz right away. Right? That's a passive one. Okay? And semi-passive has a small battery. So it tries to save the battery. It's still, basically you have to excite it, but there is a battery. So there is all three possibilities. And they get power by coupling. So there is an inductor. This is actually an inductive coupling, but there is a capacitive coupling, which when you bring it close, it becomes that way. There are three standards: 14.443, 15.693, and 340. Three different ones. This is for very close 10 centimeter reading. This is for 50 centimeter reading, and this is for NFC. Now, I didn't want to go into the details of much of this for two reasons. First of all, it's not really relevant in the level of things that we are talking about. Second thing, we have a whole course. So if you take the wireless course that I'm offering next semester, we will have a whole class on RFID. Okay? So we go into much more detail as to how all this works, how you can, what are the other issues and so on and so forth. So that is actually, I have given reference for the last offering, which was 3 years ago. And now actually 4 years total, because we offered it in 10 and we offered in 14. So 4 years. So anyway, so this is RFID stuff. What else? The last thing is the security. Any question about RFID? Yeah.
Maybe it's not a relevant question, but so it's possible now they can put a chip or a processor in the brain and control humans as well.
Oh yeah. So okay, all right. So what you're talking about, I didn't go into that particular part of IoT. There is a whole set of IoT called body area network. Okay, and there is a whole set of medical applications for similar things. They don't have to be RFID, but there are similar things which could use the devices. And so all a very simple thing. For example, previously the monitors were very passive; they were not smart. If you put a heart monitor, it will monitor, but if you get to start feeling pain, then you go to the doctor, and doctor can probably listen to the monitor and do something. Now the monitors are smart. The monitor is monitoring your heart, and it is sending that signal to your cell phone, and is calling the doctor right away. You don't have to worry about it if anything irregular happens. So that is one other application of IoT. Okay. All right. Now there are several security issues, and again, a lot more details will be in the next semester. But here are the things that people have found out can be done. Skimming, reading without the knowledge of the owner. So if you remember, this semester we had a lecture here by invited speaker in our department lecture series, who showed how you can walk behind somebody and read their cell phone by Bluetooth. Anybody remembers that lecture? Okay, so so basically summary of that lecture was that keep your Bluetooth off. But so that's the thing. Skimming is that reading without the knowledge of the owner. Eavesdropping or sniffing is the man in the middle. So that means that if I am talking to him, somebody can listen to the conversation in the middle. If suppose I am reading an RFID, somebody else can just intercept that signal and read it too. Man in the middle. Tampering, changing the data. So it is a shirt, but you change it to a shoelace or something, 10 cents, as opposed to $10, and people can do that too, right? And so that is the one. You can change the RFID. Spoofing, mimicking other source. So being other than, so you're trying to talk to this and somebody else says, I am there. Cloning, making a copy of the data. Malicious code, insertion of executable virus code. And so that is, this morning there was a news about this. They are talking about IoT viruses now. Anything that becomes smart has a virus. And so they are talking about IoT viruses and how they spread and all that. So this is already happening. Denial of service is that overwhelm the receiver's capacity. Just like you do denial of service on websites, you can do it on the readers. Killing, disable the RFID. Jamming, interfere with the smart signal, it's not a strong signal. And we teach all of this to you in the wireless class. So, if you want to learn how to jam, you have to wait. Mechanically prevent reading. And then shielding is mechanically, actually it's not electronic. So there are two ways, electronic and then mechanical. Okay, with that interesting stuff, we come to the end of this part of the lecture. So what are the things we learned? First of all, the networking has a big way to expand. Only 1% of the things are connected, and so lot of future networking development will happen in IoT. Okay. Second thing is that move is actually led right now by smart grid and energy management. So whenever you talk about IoT, it comes from the smart meter stuff, smart grid stuff, but it is going to go everywhere else, right? Third thing we learned is HomePlug. So HomePlug is very powerful. You can take up to 600 megabits over electrical power lines without installing any actually wiring, right? Then we learned about 3 standards. So 1901 was the standard for HomePlug, and 1905 is the standard to combine all of these. So hopefully when these devices start appearing, you can use any of the media at the same time, or all of the media at the same time. Then we learned about the industrial devices. They use Fieldbus in the past, and now they are going to use industrial Ethernet. And then we learned about smart cards that might use RFID, and then they are active, passive, and semi-passive. So now you should know what is active, what is passive, what is semi-passive.